I'm going to teach you some calculus today. Okay, so I've got some calc in the house tonight. So I'm going to teach you some really cool math. So in calculus, we're learning connecting f prime and f double prime with the graph of f. And the learning target is students will connect f prime and f double prime with the graph of f. Very original, okay? So, let's get some paint up in here. Alright, so, before we start Gemini, alright, we're gonna talk through some cool ass calc. So so basically what we're learning is how to say on a graph like this, you know, your typical cubic function graph, you know, with big boy behavior, we are learning how to analyze the behaviors. So on the interval, alright, let's just say this is like 2, right? So we'll just call this -2, and we'll call this one 2, right? So by making a sign chart, right, with -2 over here, and 2 over here, alright, we can see that this is given f prime, right? So we can see that from -infinity to -2, these slopes are positive, right? Or actually, this is just f. This is f, right? F. These slopes are positive, okay? And we can see that on the interval -2 to 2, these slopes are negative, and how from 2 to positive infinity, these slopes are positive. So what's happening here is by analyzing the function, we can see that we've got increasing behavior, decreasing behavior, and increasing behavior. Well, this right here is a maximum. It's a local max, all right? Actually, max is supposed to be big M, right? Over here, we've got a local minimum signified by a little m. Okay? Now, why this is important? Well, this is important because we're learning about concaves. All right, so over here, this is concave down, right? You know that it's concave down because the concave is on the down section. And here we have concave up, where our tangent lines, all right, our tangent lines are gradually going from decreasing to 0 to increasing. That means concave up, right? And over here in the middle, there is some point in which the values are neither decreasing nor increasing. And this is known as a what's it called again? Point of inflection, right? So we have a point of inflection. All right, this is all stuff that you've probably learned in pre-calc, right?
Not even close.
Well, okay. Well, this might be stuff that you're going to learn in pre-calc. So what we can do is, by using these sign charts, we can escape the need to ever look at a graph ever again to figure out end behavior. Bye. Kiss the graph goodbye. Doesn't matter anymore. Okay? And how we do this is with f derivative and f double derivative. So, I'll steal an example from homework. Okay, so we have the function f of x is equal to, and then I apologize, I have to work backwards. That's negative 2x to the third, because I never wrote down the original function, so if you'll give me a second to work backwards. I don't remember if there was a constant. Well, it doesn't matter. Plus constant, right? Now, we can actually solve for c, but that's not something I'm going to teach you right now. So plus constant. Constant doesn't matter because, as we know, the derivative of a constant is nothing. It just gets canceled out. Okay? So, actually, let me hold the microphone up to my where it's supposed to be. So, what we can do is we can take the derivative of f, right? So, f prime of x is going to be equivalent to negative 6x squared plus 12x, right? We know that in f prime, when the values are less than 0, that the graph is decreasing, and when they're greater than 0, the graph is increasing. So what we need to do is we need to find out over which intervals these are decreasing and increasing. Well, we can set this function equal to 0. So what we can do is we can actually factor out negative 6x and then factor in x minus 2, and this will give us our two zeros, one of them being 0 and one of them being 2. And then we can get f double prime, and this will tell us whether or not the function is concave down or concave up at any given point. So f double prime is just the derivative of this equation. And so we're going to use our power rule. All right, negative 6 times 2 is negative 12. Drop down this, minus 1. And then the power rule again, we distribute the 1. Minus 1 is 0, x cancels out, so plus 12. By factoring, we can factor out negative 12 from the expression and get x minus 1. And this gives us our point of inflection, actually, at 1. A point of inflection is where the changes are not going positive nor negative. On